things, because what I like about chemistry is that it explains like the actual way things really work. And when you have a theory that doesn't work for everything, then, I mean, it basically shows you how science progresses. Like I was talking about this morning, it's been known for a really long time, as far back as you could cool something down enough to liquefy oxygen, that's magnetic, and it shouldn't be. So when scientists are, presented with something like that, then that means you need either a new model or you need to tweak the one you already have. And so this is a sort of tweak on the model that we already had, which is just basically just a different way of thinking about how electrons are shared, rather than thinking about electrons being shared just between two atoms. There might be another way of thinking about it, that it's actually shared around an entire molecule. And we'll see some really good examples of that later on. Does anybody have any questions? Everyone's seen the recitation, I hope?
Yeah, but Professor, I have a question real quick.
Sure.
It has to do with the lab report. There's one where it was asking about like if a molecule has one pi bond, what hybridization will it have?
Mm-hmm.
And the whole time I thought like hybridization was just between, or it had to do with individual atoms.
Right.
So I think this whole lesson on molecular orbitals does that have to do with that question?
I guess it would. I mean, that would have to refer to a specific atom, right? Was it talking about a specific molecule?
No, it just says, in other words, if a molecule has one pi bond, what would the hybridization be? And what about two pi bonds?
Oh, but it didn't say which particular.
No, it just said generically like a molecule.
Okay. Yeah, I guess that's would be using the typical, what we've been seeing is like 4 bonds, like 8, an octet of 8 electrons being like 4 bonds. So I think that's what I meant by that question. Wasn't a very good question, obviously. So if so I think just run with that, being that would be 4 bonds would be typical, like 4 single bonds, or 1 or 3 single bonds and a double, or that sort of, or 1 single bond and 2 doubles. So yeah, just think of it in terms of carbon-carbon. I think that's probably the easiest way.
Yeah, I just ended up putting that example.
Yeah.
Okay, thanks.
Yeah, man, that's a bad question. I got to go back and fix that. That's the thing when you're trying to rush out all these labs, because there's a whole bunch we didn't get to last quarter. We only had to come up with like 6 or 7 online labs, and this term we have to come up with like about 13 or 14 of them, and then make sure that they fit within the lecture classes you're doing. So it makes it a little trickier, especially now that we've switched with a new book. The version of the book we're using now is different than the one we used before. So the order is now different, which is sort of why chapter 6 is going to be a review, because it's a lot of stuff we've covered already. Anyway, so everyone has the recitation, hopefully. I figure we just jump in with number 1, because basically it's where we left off this morning. We didn't really get to looking at, where we left off, we were going to look at oxygen molecule. But this gives us these two examples will basically show us a similar thing. How you deal with elements that have S and P orbitals and what we do with them. So do you want to start here, or would you rather start with the hybrid stuff and then come back to this, or I'll leave it up to you guys.
Start here, please.
Okay, fair enough. So whenever you're doing these sort of problems, do the atomic orbitals first. So just go back to good old S and P and D and F. And remember, these are going to be for the valence electrons. We're not dealing with the core electrons because, well, they're not involved in bonding. So in this instance, we're dealing with, can you make a diatomic molecule of silicon? Silicon. Silicon's a whole other thing. Silicon. So what's the first thing we need to figure out when we have a silicon atom here, we have a silicon atom here? What's the very first thing we need to figure out when we're coming up with the atomic orbitals for silicon over here and silicon over here? What do we need to know?
How many valence?
Yeah, how many valence electrons? Exactly. Right. How do we figure that out? What handy dandy thing do we have that will help us with that?
It's in group 4 on the periodic table.
Periodic table. Got to have a periodic table. It's in group 4, exactly. So how many valence electrons does it have?
4.
Got 4. It's right under carbon. So that right there, that tells you, well, we should know a lot about carbon because we've been dealing with it a lot. It's in practically all interesting molecules. And silicon's right below it, so it's got to have 4 valence electrons too. And here you notice that we're starting with 3s. Why are we starting with 3s and 3p? How come we're not filling in the other orbitals first? 1s and 2s and 2p. How come we're not filling those in?
Is it because those are core electrons?
Exactly. Man, killing it today. Yes, those are core electrons. So we don't really care about them because they're not involved in bonding. So they're not going to be a part of making the molecule. They're going to be held onto by silicon. So that's going to increase the electron density around the atom. But remember, bonding is electron density between the atoms. So core electrons have nothing to do with that. So they are only involved in electron density around the atom, not between. So we only want the electrons in the outermost shell, i.e. the valence electrons, because those are the ones that are going to be shared between atoms. So with carbon, that started with 2s and 2p. But now we've moved one down. We've moved one row down. That's a new period. That means that new shell. And so now the valence electrons, still the same number, still 4, but instead of being 2s and 2p, now they're 3s and 3p. When you go down one more, they're 4s and 4p. You go down one more, it's 5s and 5p. I mean, that's how the valence system works, right? So we have 4. So where are we going to put our 4 electrons in our atomic orbital? Where do we put them? We got 4 to put them in. So where do we put them? And that's so here, this atomic orbital and this atomic orbital. So this is exactly the sort of question you would get on a test. So I'm giving you which orbitals we're interested in, atomic orbitals, and I'm showing you the molecular orbitals that we're going to fill in. I don't want you to have to memorize that. It's confusing enough already. But you are going to have to figure out how many valence electrons. We've already established it's 4. And where do they go?
You follow Hund's rule, so you start with the 3s and just fill it up.
Yep, exactly. So where do we, how do we do that?
2 and 3s, 1 up, 1 down,
Yep.
and then 1 up, 1 up, and 3p.
One,
Separate
two,
order.
that's 4. And that should remind you that looks like carbon, right? We got a pair and then 2 in P by themselves. And so what's going to go on the other side? So that's our first atom. What about the other side?
Wouldn't it be the same thing?
Yes, it would. Yeah, it's the same thing. It's just it's silicon on one side, it's silicon on the other side. So it's exactly the same on the other side. And the nice thing about the molecular orbital model is that it once you have your electrons, it's fairly straightforward to figuring out where they go. So notice that we have 4 in s orbitals and we have 4 in p orbitals. So that's basically where they're going to go in the molecular orbital as well. So now we've established what one atom looks like, what the other atom looks like. Now it's time to fill in our molecular orbital in the middle. So where do we start?
The lowest bonding energy.
Always start at the lowest bonding energy. And remember, sigma is the lowest. Sigma is the most stable bond. And so bonding for sigma is the very first one. And how many electrons do we put in there?
2.
2. 1, 2. All right, I got 6 left. Where do the next 2 go? So I put my first 2 in sigma. Where do the next 2 go?
I can't tell if you're supposed to go to the anti-bonding or the 3p pi.
Which one's lower?
The pi.
Are you sure?
Oh no, actually visually it's a anti-bonding sigma.
It is. It is. So how many do we put in there?
2.
2. We also put 2 in there. So 1, 2. Now I have 4 left. So where do they go?
You fill up the 3p pi.
In which order?
You first put 1 going in the positive spin.
Mm-hmm.
Fill up the positive spin first.
Right. Where's the second one? Where's the next one go?
To the orbital to the right.
That's right. Very good. Because remember, they're called degenerate orbitals, not because they do anything, horrific or anything. They're degenerates. Degenerate just means they're the same energy. And so if they're the same energy, then you put an electron in one, then you put an electron in the other one to keep them far apart from each other. And then you come back and fill them in. So you have 1, 2. So I have 2 left. So where do the next 2 go?
You put the down arrow or negative spin on the left orbital and then the right orbital.
Right. And then that's my 8. Then I'm done. So then basically now, what is our bond order going to be?
Are you just listing them from bottom to top or from lowest to highest energy when you are writing out the bond order?
The bond order is simply how many electrons are bonding and how many electrons are anti-bonding. So how many electrons do we have in bonding orbitals? Now remember, we're just looking at the molecular orbitals at this point.
So would we be doing 6 minus 2
Yeah.
divided by 2?
So where are 6 bonding orbitals or 6 bonding electrons?
The 6 bonding electron, well, 2 of the bonding electrons would be in the sigma.
Yep. There's 2.
And then 4 of the electrons will be in the pi orbitals.
Yep. So that's 6 total that are bonding. And then we subtract the ones that aren't. So which ones aren't bonding?
The sigma star.
Yes. Those are not. Those are actually I shouldn't say they're not bonding. They're anti-bonding. So we like literally subtract those. And then we divide that by 2. So what's our bond order then?
2.
2. So that predicts there should be a double bond between the 2 silicons. And so the next question is this going to be magnetic or not magnetic? What do you think? Do you remember how to determine whether something's magnetic or not?
No.
It had to do with spin.
Never mind.
Anyone help them? How do we know if something's magnetic or not? There's something to do with electrons, because it's chemistry. Got to have something to do with electrons. And it has to do with spin.
If
It's
they're both
magnetic.
opposing spins,
So if I have electrons with opposing spins, does that mean it's going to be magnetic or not?
magnetic because it has to be positive and negative, right? Opposites attract, that type of thing.
Well, remember, yes, opposites attract, but do I need to have, so with an atom with opposite spins, does that sort of cancel each other out? So do I want more electrons with paired spins or more electrons with unpaired spins?
The waves would, oh, it would cancel if it was positive and negative.
Right. So if I have paired spins, that basically means I am not magnetic. That means I'm diamagnetic. I'm not attracted to a magnetic field because all the electrons in the atom are all paired up. So but that means they're not going anywhere. They basically cancel each other out. Each spinning electron creates a small magnetic dipole, just like the difference in charge is an electrical dipole. A difference in spin is a magnetic dipole. And so if I have everything spinning in the same direction, it increases my magnetic dipole. If everything is paired up, just like a molecule with all its bond dipoles pointing in opposite directions cancels each other out. Same is true for magnetism. So if all my electrons are paired up spinning in opposite directions, they all cancel each other out and I have no net magnetic dipole. So does this molecule have all paired electrons or does it have unpaired electrons?
Paired.
Yeah, they're all paired, right? All the bonding electrons are paired. All the anti-bonding electrons are paired. So there's no net magnetic dipole. So it's diamagnetic.
I have a question,
So
Professor.
not magnetic. See.
So with Hund's rule, where we have to fill up each orbital before we move on to the next, then how do we get, what is what would this molecule be attracted to if it's not filled up? Because that would just be a positive spin. So there would just be a bunch of positive spins. Does that make sense?
Sorry, I sort of missed the middle of that. So you're asking, like, when would it be magnetic?
Yeah, so when it's magnetic, and that would just tell me there's only one electron in the orbital, but that electron would be pointing up. So that would make what I'm thinking is that everything with one electron is going to be a positive electric field. So how would anything...
Positive magnetic field.
Yeah, positive magnetic field. So how do we get a negative magnetic field if...
Well, there's no such thing, really.
Okay.
I mean, yeah.
Okay.
either you have a net magnetic moment or you don't.
Okay.
Yeah. So either, because it's the same thing. I mean, if they're all spinning in one direction, if that atom is basically, upside down, they're all spinning in that direction. I mean, they're all spinning. It's the direction that they're spinning, not really whether they're pointing up or down. It's whether they're spinning in one direction or spinning in the other one.
Okay.
Yeah.
What are the types of magnetic? It's diamagnetic. And what was
if I remember correctly, it's diamagnetic for no magnetic and paramagnetic for C on the magnetic. I think that someone might want to check me on that. I'm constantly mixing that up. I'm pretty sure that's how it works. I hope. Someone can double check me. But basically, yeah, here we can see that since all of the electrons are paired, then that net spin is nil, 0. So we could put a magnet in front of this and it's not going to go towards either pole. All right, shall we do the next one? Let me clear everything. So here we have a real molecule. Here we have sulfur, oxygen, and it is a cation this time. So on one side, we are going to have sulfur, and on this side, we're going to have oxygen plus. And then we'll see when we put them together, what are we going to get? So in this instance, so just going back to the way we did it the last time, what's the first thing we need to do?
Use your periodic table to find out how many valence electrons.
Yep, exactly. So what group? Actually, sulfur and oxygen are in the same group. Which group is that?
I had to walk away, but I'm going to guess 6.
You have to walk away? What was that?
I had to walk away really quick from my periodic table, but I think it's 6.
It is 6. That's right. Oxygen is 6 valence electrons, and sulfur is right below it. So as you can see here, we know that this side is going to be sulfur because it's 3s, and this side is going to be oxygen because it's 2. So the valence electrons for oxygen start in its outer shell, which is the second one, and the valence electrons for sulfur start in the third shell because that's the outer limits for sulfur. That's where its electrons are furthest away, is in the third shell. So how many, we know that they're in the 6th group, how many valence electrons does each one of them have?
The sulfur will have 6, but the oxygen will have 5.
Right, yeah, sulfur's got 6. Sulfur has its full 6 because it is an atom. It is not an ion. So if it's an atom, it's neutrally charged. It has 6 valence electrons, 6, and it has all 6 of them here. Oxygen's missing 1. So oxygen is an ion here, a monatomic ion. So a monatomic cation, which oxygen generally will not be, because oxygen really, really, really likes electrons. So it's lost an electron, so it now has 5. All right, so sulfur. How are we going to fill in our sulfur electrons? Where do we start?
Fill up your s orbital with 2 electrons.
Yep. 1, 2. There's my first 2. I got 4 left.
And proceed with the p. You have 4, so 1 in each.
Yep. Pointing which direction?
All pointing up.
All pointing up, right. 1, 2, 3, and then my 4th one.
Back in the first one, pointing down.
Yeah, there you go. And realistically, you could put that one anywhere because they are degenerate. So it could go in the X, the Y, or the Z. It really doesn't matter. So there we go, 6 electrons. Now on the oxygen side, we only have 5. So where are those going to go?
Same thing, fill up the S shell with 2.
Okay, 1, 2, okay.
And then all pointing up on the P shell.
1, 2, 3. Right, so those are all completely unpaired in the oxygen. Usually we have 2 there, just like with sulfur. But since we're missing one, that is going to change it up. So we lose one of the P's. All right, so we have our S, we have our sulfur, we have our oxygen plus. Now we move into the molecular orbitals. So total number of electrons we need to fill in is 11. 6 from sulfur, 5 from oxygen plus. So where do we start?
The 3s sigma.
Okay. 1, do I put 2 in there?
Yes, 2.
Okay. All right, now I got 9.
And then you put 2 more in 3s sigma star.
Okay. 1, 2. Now I got 7.
2 more in 3 pi sigma.
1, 2. Now I got 5.
And then for the 3 p pi sigma, you're going to start one at a time. 1 electron, and then the other one in the right orbital.
Okay. Both pointing up, right?
And then go back to the left orbital, point down, and then go to the right and point down.
Okay, so 2, 4, 6, 8, 9, 10. Okay.
And then one last one in the 3p pi star.
Star. Okay. 11. So 2, 4, 6, 11. Yes. Okay. We're done. So what's my bond order?
Is it 2.5?
Well, take me through it. How did you come to that?
Oh, okay. So there's 2, 4, 6, 8. So there's 8. Is it called regular bonds?
Do you just say bonding? Just 3
Okay.
bonding?
Pre-bonding. So 8.
No,
pre-bonding.
don't. I'm sorry, not pre-bonding. Because tongue wasn't working. Just bonding. Just look for bonding orbitals.
Okay. So of the bonding orbitals, there's 2, 4, 6, 8.
2, 6, 8. So we have 8 bonding. And then how many in anti-bonding?
3.
3.
And then we're going to divide that by 2.
That's 2.5. So it's the bond order is 2.5. And is the molecule going to be diamagnetic or paramagnetic?
Paramagnetic, since you have an unpaired electron at the
Right.
anti-bonding.
Exactly. Now, if you wonder why oxygen is paramagnetic, if we just substitute oxygen over there and oxygen over here, that would give us just one more electron, right? That would give us a total of 12 electrons rather than 11. And watch where does that 12th one go? So now I have 2 oxygens, each with 6 valence electrons. I've got 11 valence electrons in my molecular orbital. So I need to place one more. Where does it go?
It would go to the right of the 3p pi star.
Yep, it would go right there. So now I have 2 unpaired electrons, which makes it even more paramagnetic. Also, what does it do to the bond order now that I've added another electron?
It decreases it.
Yeah, it does. Why does it do that?
Well, you would now be replacing, if we go back to your equation, the 8 minus 3, you would be replacing the 8 minus 3 with 8 minus 4.
8 minus 4 now. So instead of being a bond order of 2.5, it's actually a bond order of 2. And we know that's true with oxygen because we have oxygen looks like this, right? It has a double bond. So that is indeed true. So what I'd want to do now is basically let's draw what the Lewis structure of SO plus looks like and see if we can make sense of that bond order of 2.5. So what I'm going to do is clear this and then just share a whiteboard. So let's just see if we can do this one. All right, so I have right now, so we're just doing SO plus. So I've got my sulfur, whoops, a little wider than that. There's my sulfur, there's my oxygen, there's my bond. So SO plus. So what's going to be the total number of valence electrons? We already should know this, right?
11.
Should be 11, right, exactly. And how many do we have in bonds?
2.
So how many do we have left to play with?
9.
So we have 9 electrons left to play with. So remember, we want to give an octet, or try and give an octet to both of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's not going to work. Sulfur has a full octet. How many does oxygen have? How many total electrons does oxygen have in this particular model?
5.
Yeah, it's only got 5, so that's not going to work. So what do we do? How do we get around that?
Professor, so do we say we add a pi bond or just make a double bond?
In this instance, yeah, we're just making bonds.
Okay.
Yeah, we're just making bonds. We would say sigma and pi, though. That's fine. Yeah. The thing to remember when we're dealing with the molecular orbitals, just because we're putting them in like sigma and pi, basically all it's saying is that how many electrons are in bonding regions, how many are in anti-bonding regions. And so that just tells us how many electrons are involved in bonding, because it's a different way of looking at the molecule. It's these electrons basically are being shared around the molecule, and we're trying to figure out how many are involved in bonding and how many aren't. So it's not so much about electron density in a particular place. It's just of all the electrons in this molecule, how many are doing the bonding thing and how many aren't. So we sort of get away from just strictly thinking about sigma and pi. Here we can think about sigma and pi. So, right, so we've got, so S is happy, sulfur's happy, oxygen not very happy. How do we make sure each of them gets as many electrons as they need?
We would move a lone pair from sulfur to make a double bond between
Yeah.
sulfur and oxygen.
Put that in the middle. So that makes another bond. And I will take out, oops, I want an eraser. I'll take out that lone pair. So now sulfur's still happy. Sulfur still has 8. How many does oxygen have now?
Seven.
Oxygen has 7, right. So oxygen still isn't happy. So what we do in this situation, we basically take one electron from sulfur and just have it be shared. So basically we would form a resonance structure. So this would be one resonance structure where sulfur is, oh, actually let's figure out what the charges are. So the charges on sulfur wouldn't have a charge, right? Because it has 6 valence electrons. And how many valence electrons does it have in this particular model?
Six.
Has 6. So that sulfur is not charged. What about the oxygen? How many valence electrons does the oxygen have?
Five.
5. So it should have 6, but it only has 5. So there's a plus charge there. Now, which one is more electronegative, oxygen or sulfur?
Oxygen.
Oxygen. So if there's going to be a charge, if there's going to be a positive charge, where is it more likely to be, on the sulfur or on the oxygen?
So that means which one is more likely to lose an electron?
Right.
So wouldn't sulfur usually be more likely to lose an electron because oxygen is always trying to grab?
Exactly. So if we move one of these electrons to oxygen, now it has a full complement. So we'll take that electron away. Now it isn't charged anymore, and now sulfur is, which is more likely. Now sulfur has the positive charge. But you can see we have 2 different versions of the same molecule. And when we have that, what do we do?
Is this like the bonus question where we draw the electron going back and forth quickly?
Mm-hmm. Yeah, so when we have 2 different versions, we have 2 different versions of the same molecule, right? The other one was the original, 1, 2, 3, 4. 1, 2, 3. So the oxygen was plus. So each of these is possible. This one is a little more likely than the second one because oxygen is more electronegative than sulfur is. But each of them, you can make a case for each of them being present. So you remember what we then do when we have that situation? What can we draw in the place of either one of those? You remember what we called it? We have this structure and we have this structure, and we say they're resonance. It could be either one. Or we can take the two of them and bring them together, and when we bring them together, what do we draw? Do you remember what it was called?
Hybrid structure.
Yes, I was just about to say it. You got it for me. Excellent. Yeah, we call it a hybrid structure. And what would the hybrid structure look like? Look kind of odd, right? So basically it would look something like this. So we have, oops, we have our sulfur here, oxygen there. 1, 2, 3, 1, 2, 3. Where does that extra electron go? So I'm not putting it here, and I'm not putting it there. So where does it go?
Are we gonna like draw something to show that it's moving, like a dotted line or something?
Yeah, exactly. We just put a dotted line, like 1, 2, like that, with a single electron on it. And the positive charge basically would be shared between them. Now, have a look and see how many electrons are being shared between the sulfur and the oxygen.
1.
Total.
5.
5. 5 electrons are being shared. So they're sharing 5 electrons, and each of them have 3, so they can claim an octet. So each of them has an octet. But what does that mean when you're sharing 5 electrons? What's your bond order? So it's sharing these two, sharing these two, and it's sharing that one for a total of 5 shared electrons. What's the bond order when you've got 5 shared electrons?
I'm just guessing. Would it be 4 minus 1 divided by 2?
4 minus 1 divided by 2? Why minus? You're sharing 5. Why are you subtracting the 5th one?
Because I thought we were doing that formula with when you're dividing by 2, you take the bond.
Oh, we're not doing that now because we're drawing a Lewis structure. So whenever we draw a Lewis structure, if we're sharing electrons, we make a bond, right? So I'm sharing 2 electrons there, they make 1 bond. I'm sharing another 2, that makes a double bond. Now I'm sharing 5. So what's the bond order now? Because we're not dealing with molecular orbitals here. We're just dealing with drawn a picture of 2 atoms sharing 5 electrons. What bond order does that give me? If they were sharing 2, it would be 1. If they were sharing 4, it'd be 2. If they were sharing 6, it would be 3. Now they're sharing 5.
2.5.
2.5, right. And what did the molecular orbital diagram predict would be the bond order for this molecule? Whoops. Uh-oh.
It was 2.5.
Where did it go? I did something. Are you still with me?
Yeah.
Something went. haywire with my computer here. There we go. Man, it looks like I I signed out or something. I had to sign back in. Yeah, so the molecular orbital diagram predicted it would have a bond order of 2.5. And as you can see, when you draw the Lewis diagram, that is the bond order you get. It's 2.5 for this molecule because it's got a double bond between the sulfur and the oxygen, yet there's another electron that is being loosely shared between them. And so when you think about bonds, you're just thinking about how many electrons are being shared. Where is the electron density? And in this instance, there's an electron density of 5 electrons moving back and forth, being shared between the two atoms. And so we call that a bond order of 2.5. So we can see that they agree with each other. So does this make sense to everybody? How you can get an order of 1/2 when we're dealing with these hybrid drawings? Because in one, we've got 2, we got a double bond there. And in the other one, we have the same double bond, but the electron's in a different place. And so when we average them out, they're in neither place, but they're in between. They're being shared between the two. I guess that means everyone agrees and everyone understands. Now, really, if you have any questions about this, now it's like this is the perfect time to be asking.
So, Professor, when do we do this versus the equation that I was talking about, the divided by 2?
Oh, whether or not I may ask, like this may be the perfect kind of test question. I'll give you a molecule like this, and say, draw the Lewis structure of it. Is there more than one Lewis structure you can draw? If so, give the hybrid structure, and then predict what the bond order is based on your hybrid Lewis structure. Then make a molecular orbital diagram. Fill in the electrons. Does that bond order agree with your Lewis structure? So this is a really good question. Expect a question quite like this on the test. I like this question a lot, so I think I'll probably give something like it.
And they are always going to agree unless you did
We
something.
hope.
Okay.
We hope they do. They better. Yeah, they should. They should. Like when we look at nitrogen, nitrogen, as we know, should have a triple bond, right? Nitrogen looks like that. And when you do your orbital diagram, you should get 8 electrons in bonding orbitals and 2 not in bonding orbitals, in anti-bonding orbitals. And so you should get a bond order of 3. Should. So let me go back to, all right. So who's had a chance to look at the rest of it? What would you like to do next? The rest of it's more straightforward stuff. Yes.
So say we have a more like a bigger complex molecule.
Mm-hmm.
Are you asking to find the areas, like certain areas of that molecule, or the whole, the molecule as a whole to find the,
Oh yeah, you mean you do this, I mean you make the molecular orbital diagram for a particular bond.
Okay.
Yeah. So yeah, the molecular orbital diagram for an entire molecule would be more complicated. But I mean you can still do it. Basically because the molecular orbital diagram tells you what the bond order of the whole thing would be. Like how many electrons are bonding, how many are anti-bonding. So you could do that, but yeah, mostly it'll be something like this, predicting a particular pair. I don't think I'll have another look at the textbook. I don't think they go into. I mean, they give some examples of stuff like benzene, C6H6, which is something we're going to talk about on Thursday. But I don't think they ask you to solve it, like questions like that. We'll talk about how to do that, but I won't be asking about that. This is hard enough, right? I mean, all right. Well, what do people want to look at next? These are more or less straight up questions, very similar to the ones we had last week. I have underlined all of the central atoms. So I think I did, except for the last one. I should be able to figure out which is the central atom in SBF5. And then, yeah, draw your Lewis structure. So when I ask for approximate bond angles, all I'm asking for, is it going to be less than ideal, more than ideal, or is it going to be ideal? That's it. You don't have to give an exact number, because I mean, who knows what the exact number is going to be. Just based on the picture you drew, more, less, or ideal. So it's helpful to know what are the ideal bond angles for the different shapes. And there's really only three. There's 90 degrees, 120 degrees, and 109.5. That's it. Those are the only three angles you need to know. So everyone's cool with these? What about this last one?
Yeah, I was going to ask you about the last question, unhybridized. So that's just like the regular orbital?
Regular old atomic orbital, yes.
Okay.
So since both nitrogens are the same, just pick, they're both going to be exactly the same. They're going to have the same hybridization. They have the same number of valence electrons. So the hybridizations will be the same. The atomic orbitals will be the same. The hybridized orbitals will be the same. And then the previous question, I think that's caffeine. I can't remember. Yeah, basically the same sort of thing. Just go in there, and what it's asking for is what's the, whoops, let me go back. For this nitrogen here, damn it. Get in there. There we go. For this nitrogen, stupid computer. Man, it's not letting me.
We could only see like two small screens. I'm not sure if you noticed that.
Oh, okay. Oh, I see what's going on. How about now?
That works.
Yeah, I shared the wrong thing. Yeah, my laptop has two screens on it, and so I was sharing the wrong one. I apologize profusely. Yeah, so for each of these atoms with an arrow pointing next to it, what hybridization is it? sp, sp2, sp3, sp3d, whatever it needs to be. And then what's the approximate bond angle? Is it equal to ideal? Is it more than ideal? Is it less than ideal? So the bond angle here would be the hydrogen, nitrogen, carbon, that angle. For 2 would be the fluorine, bromine, fluorine, they'll all be the same. For the sulfur here, fluorine, sulfur, fluorine. And then answer the same questions for this nitrogen and that oxygen. You're just basically answering the same questions. Give me the hybridization and the bond angles for each one. So does anyone need any like little push with any of these, or you guys just you're just ready to go?
Professor, sorry, I'm having a little trouble still understanding like bond angles. So,
Sure.
if you would, could you go over one of them, please?
Yeah, no problem. This is why we're here. I beg you to ask questions, and I have a question. I'm a happy guy. Yeah, let's do one. Let's just look at the first one. So, what shape would that be? That's the first thing we need to ask ourselves. Is that we have no idea what the bond angle is going to be until we know what shape that is. And so we use our Axe body spray formula to figure out what the shape is. So my central atom is sulfur. So that's my A. X is the number of atoms surrounding it. So how many is that?
4.
So AX4, and then E is the number of lone pairs of E electrons. So how many is that?
1.
1. So A4, AX4E. And I go to my table because I can't remember anything. And I look for AX4E. Well, that means it has 5 regions of electron density. That means it's in the trigonal bipyramidal. That is the overall geometry. Trigonal bipyramidal, that means 5 regions. That does not mean that the particular molecule is that, because shape and geometry are different. So inside this particular group of shapes, I have ones with 5 atoms. I have ones with 4 atoms and an electron. I have ones with 3 atoms and 2 electrons. And I have one with 2 atoms and 3 electrons. So I'm looking for this one, and I look it up, and that is a seesaw. Okay. So I have a seesaw shape. And it says that, clear this out. So I've got a seesaw shape. So you look at what that would look like. So you've got sort of look like this. It has the lone pair on the top, and then it has the 2 fluorines out, and then the other one sort of at a different angle. And you look at the angles, and ideally, what it would look like is you'd have your lone pair on top and a fluorine on the bottom, and then fluorine, fluorine, fluorine around, 1, 2, 3. These would be 90-degree angles, and these would be 120-degree angles. So ideally, fluorine, sulfur, fluorine, 1, 2, 3, would be 120 degrees. Is that right? No, sorry, it would be 90 degrees. Because I have sulfur, fluorine, and 1, 2, 3. So, right. So that angle ideally should be 120 degrees. The question is, will it be more than that now? Will it be less than that? Or will it be the same?
the same?
Actually be just a tiny bit less, because these push the fluorines a little bit closer together and reduces that angle just a little bit. Not by much, but just a little bit.
Oh,
So
okay.
so you just say it's a little, so the ideally it's to be a little bit smaller. So you just say a little bit less than 120. And it actually has that, as a helpful hint, it actually has that in the table. When you look at it, it says the axial angle is a little bit less than 90 and the equatorial angle is a little bit less than 120. So you could say it's a little bit less.
Okay, thank you so much, Professor.
Oh, no problem. Oh, what's the sulfur hybridization? We didn't do that part. What's the hybridization on sulfur? Sulfur has 5 regions of electron density. What hybridization is that?
SP3D?
Yes, exactly. sp3d. So it needs 5 places to put electrons. Excellent. Okay, yeah, excellent question. Anybody else before we wrap it up? It'll be like an early day today. Anybody else with a question before we go? So you're cool with how to do the rest of them then?
Pretty good. If not, I'll see you tomorrow in your office hours.
Right. Right. Yeah. So yeah, if someone reminded me, yeah, tomorrow is Veterans Day, but since I'm such a hard worker and committed to learning, I will be there at 11. Okay. So if you have any questions about this or anything else, let me know. We'll get together. Okay.
Thank you, Professor.
All right. Thank you, people.
Thank you.
Stay well. I'll talk to you soon.